Welcome to the class. We have seen what do we mean Brayton cycle and how does an ideal Brayton cycle thermodynamically would look like. We have also done calculation for the ideal Brayton cycle and also for the Brayton cycle with the non-ideal components. Now we are going to see some attachments to the Brayton cycle, and today's class we are going to deal among those as heat exchanger and reheater. So let us start. Practically, let us see first Brayton cycle with heat exchanger. So schematic, we have seen it when we were considering different configurations. Here we will first have a compressor as we would have in general. So air will come first into the compressor, and then while going it towards the combustion chamber, it will get heated from the state 2 to state 3, and then it will appear into a combustion chamber. Then it will have combustion process from state 3 to state 4. Then at 4 it will enter into a gas turbine. So this is gas turbine, and then the process ends for the expansion, isentropic expansion in state 5. So then the gas at state 5 gives its heat to the air which is going into the combustion chamber, and this heat transfer will take place from state 5 to state 6, and this heat transfer unit is called as heat exchanger. So this is turbine. This is how we have seen as an arrangement or schematic for Brayton cycle with heat exchanger, where this is the exclusive heat exchanger we are going to see. Now we will see about the thermodynamic cycle. So the thermodynamic cycle with heat exchanger would not get largely altered, but we have to show point number 4 and 6. So let us plot T and S. Then we have 1 to 2 isentropic compression, then 2 to 3 is heat transfer in the heat exchanger, 3 to 4 is heat addition in the combustion chamber. We should note that the pressure in the heat exchanger here and pressure in the combustion chamber here is same, and both are entertaining constant pressure heat interaction. So 4 to 5 is turbine, and 5 to 6 is heat transfer in heat exchanger on gas side, and this is for air side, and 6 to 1 is heat rejection, and again we have pressure at 5, 6 and 1 is same. So looking at this, we can draw PV diagram for Brayton cycle with heat exchanger, and then we can show that 1 to 2 is isentropic compression, 2 to 3 is heat addition into the heat exchanger, 3 to 4 is heat addition into the combustion chamber, and then we have 4 to 5 is isentropic expansion, and 5 to 6 is the heat addition into the heat rejection into the heat exchanger. So this is how we have the schematic and thermodynamic cycle. The point which we should note here, that the temperature at 2 has to be lower than temperature at 5. That means temperature at the exit of compressor has to be lower than temperature at the exit of turbine to implement the heat exchanger. So, this remains the criteria to implement the heat exchanger. Practically we have seen that when we are working on a pressure ratio which is optimum pressure ratio, then in that case we have seen that T2 is equal to T5 as per this diagram. So, now since this remains the constraint, so we should work on the pressure ratios which are lower than RP optimum, and those pressure ratios would lead to T2 to be less than T5, and then we can implement the heat exchanger. So, this is what we should remember as the constraint to implement heat exchanger. The idea of putting heat exchanger is that instead of passing the air from station 2 into the combustion chamber and heating it to 4, we are passing it at the station 3 to heat it till 4. So, practically the mean temperature of heat addition would get increased. Now, instead of having air heated from 2 to 4, it got heated from 3 to 4. So, mean temperature of heat addition has increased. Parallelly, mean temperature of heat rejection has also decreased. Since we did not reject the heat from 5 to 1, we rejected the heat from 6 to 1. So, since mean temperature of heat addition would increase and mean temperature of heat rejection would decrease, the efficiency of Brayton cycle practically will increase. So, importance of heat exchanger is to increase the efficiency, and this remains the constraint for implementation of heat exchanger. So, now we will again plot TS diagram for the heat exchanger so as to calculate heat exchanger calculations. So, this is TS. So, 1 to 2 to 3 to 4 to 5 to 6. So, in the heat exchanger we should say that the amount of heat gained by the air at exit of compressor in heat exchanger is equal to heat lost by gas, but practically we are going to work with air standard. So, this is also air, this is also air. So, but in general this will be the combustion products which will be giving heat to the air. So, heat lost by the gas at exit of the turbine in the heat exchanger. So, this is H3 minus H2, this is H3 minus H2, which is equal to H5 minus H6. So, we know that Cp into T3 minus T2 is equal to Cp into T5 minus T6. So, practically we will get T3 minus T2 is equal to T5 minus T6. So, this is the balance of heat equation in the heat exchanger. If the heat exchanger would not be ideal, then we have to implement the effectiveness of heat exchanger, which is said as eta He, and it is the ratio of actual heat transfer divided by maximum possible heat transfer. So actual heat transfer is H3 minus H2 and maximum possible heat transfer is H5 minus H2, or otherwise this is also actual heat transfer is H5 minus H6 and maximum possible heat transfer is H3 same H5 minus H2. Now let us consider the fact that we have an ideal heat exchanger having effectiveness 1. So we can mention H3 minus H2 divided by H5 minus H2 is equal to 1, and this leads to H3 minus H2 is equal to H5 minus H2. So this leads to H3 is equal to H5, or practically T3 is equal to T5. And secondly, we can also write as H5 minus H6 divided by H5 minus H2 is equal to 1, since this is the second formulation for heat effectiveness of heat exchanger. So we have H5 minus H6 is equal to H5 minus H2, and then that would lead to H6 is equal to H2, and this leads to T6 is equal to T2. So this remains the outcome of having ideal heat exchanger. So we can write down the ideal heat exchanger cycle as this TS diagram, and in that ideal heat exchanger cycle we will have like this 1 to 2 and 2 to 3, but T3 is equal to T5, and 5 to 6, but 6 is equal to 2. So this is how the ideal heat exchanger based Brayton cycle would look like. Then let us move ahead and find out the work interaction and heat interaction in the process of heat exchanger. So here again we will plot now the ideal heat exchanger such that we have TS diagram 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. So this is TS diagram. So now here we can mention WC compressor work in the presence of heat exchanger. There is no change, so compressor work is still H2 minus H1 or Cp into T2 minus T1, and turbine work is same, which is H4 minus H5, and that is Cp into T4 minus T5. So we have W net, which is Wt minus Wc, is same with and without heat exchanger. So it is equal to Cp into T4 minus T5 minus T2 plus T1. So this doesn't alter. The thing which alters is Qin, and Qin is equal to H4 minus H3, and then that is equal to Cp into T4 minus T3. So this alters the efficiency, which is W net upon Qin, and W net is equal to Cp into T4 minus T5 minus T2 plus T1 divided by Cp into T4 minus T3. So this Qn has got decreased in the presence of heat exchanger, W net has not altered. So efficiency increases with attachment of heat exchanger, but W net remains constant or same with heat exchanger. This is the outcome of this interaction. Now let us see the same thing in terms of plot. Here we can further simplify this expression and we can write down it, rather we can simplify the expression for W net, and that can be Cp into T4 minus T5 minus T2 plus T1. We can take T1 common, so W net is equal to Cp T1 into T4 by T1 minus T5 by T1 minus T2 by T1 plus 1, and then this is equal to Cp T1 T4 by T1 is beta, since we have said T4 by T1 is equal to T max by T min, and that is beta for us, and T5 by T1 can be said as T5 by T4 into T4 by T1 minus T2 by T1 plus 1. So this can be again written as beta T4 by T1, T5 by T4 over here is 1 upon beta, and then this T4 by T1, T5 by T4 is 1 upon Rp raised to gamma minus 1 upon gamma, and T4 by T1 is beta, and then this is Rp raised to gamma minus 1 upon gamma, and then we have plus 1. Let us say C is equal to Rp raised to gamma minus 1 upon gamma. So we can write down W net as Cpt1 into beta minus beta upon C minus C plus 1. So this would be the simplified formula for W net, and we can use this formula for analyzing the plot, or we can rather use this to plot W net versus rather non-dimensional W net as W net upon Cpt1 versus Rp. So we can plot it for different Rps. Obviously we mean here that we are plotting with respect to Rp, since C contains Rp and we are working with constant beta and constant T1. So we get a plot like this. This is the plot for different betas. So this is beta 1, this is beta 2, this is beta 3, and this is beta 4. Parallelly, if we plot efficiency versus Rp, then we can see that first we will plot the efficiency for heat exchanger without attachment. This is heat exchanger for Brayton cycle without heat exchanger. This is without heat exchanger. We had seen this plot earlier, and this is efficiency variation with respect to Rp, but now this efficiency would have beta in it. The heat exchange, the Brayton cycle efficiency is independent of beta. It is only function of Rp, without heat exchanger, but now with heat exchanger it becomes function of beta. So we have to plot it for different betas. So in this case efficiency is like this. So this efficiency is for beta 1, beta 2, beta 3, beta 4. So at higher RPs efficiency would decrease. So at lower RPs only we can use the heat exchange process, and that limiting RP depends upon beta. So this is the understanding from the Brayton cycle with heat exchanger. So let us move ahead and see Brayton cycle with reheat. So we will first plot this schematic, and schematic is as expected, except that we are having an attachment of reheater. We will have air entering in 1 and leaving at station 2 in the compressor. Then we have combustion chamber from 2 to 3, and then we have a turbine which is called as high pressure turbine. The exit of high pressure turbine is given to a again heat transfer unit, and that is called as reheater, and after reheating air will pass into again a turbine, and then that turbine is low pressure turbine, and then air would go out. So this is the schematic of Brayton cycle with different components where an extra component of reheater is added. Now we have to draw the thermodynamic cycle, and thermodynamic cycle, which is at this moment we will plot as TS diagram, is 1 to 2 is compression process, 2 to 3 is heat addition in the combustion chamber, 3 to 4 is high pressure turbine, 4 to 5 is reheater, 5 to 6 is low pressure turbine, and 6 to 1 is the heat rejection process. Now we will also plot the PV diagram for this, and PV diagram will be 1 to 2 isentropic compression, 2 to 3 is heat addition in the combustion chamber, 3 to 4 is high pressure turbine expansion, 4 to 5 is heat addition in reheater, and 5 to 6 is expansion in low pressure turbine, and then 6 to 1 is heat rejection. So this is how we have different processes in the Brayton cycle with reheater attachment. As what we see here, we if would not have implemented the reheater, then we would have expansion in only one turbine. So without reheater we have only one turbine, but with reheater we will have many turbines, and practically as per this diagram we are saying that we have two turbines. So this is the new attachment. So this is the new understanding. Further, one should know one more thing, that the reheater is heating the gas or air, and then that the temperature at the exit of reheater in general would be same as the temperature at the exit of combustion chamber, unless otherwise prescribed or required. We would have this T5 will be different from T3, but otherwise T5 is equal to T3. And reheater also does the constant pressure heat addition. So this is one thing. Second, reheater adds heat at pressure constant process or isobaric process, and in general T3 is equal to T5. So, let us see work and heat interactions in the reheating process or Brayton cycle with reheater. Here we can say WC is compressor work, which is H2 minus H1. There is only one compressor, so it is only H2 minus H1. So we can write it as Cp into T2 minus T1. For the turbine, there are two turbines, so we will write Wt high pressure turbine plus Wt low pressure turbine. So we will have Wt is equal to H3 minus H4 plus H5 minus H6, and then this can be further said as Cp into T3 minus T4 plus T5 minus T6. So this is the Wt. Now we can write W net, and W net is equal to Wt minus Wc. Further we can say heat addition. Now heat additions are also 2, and one heat addition is in the combustion chamber. So Q in Cc plus Q in reheater. So Q in is equal to Q in Cc, and Q in Cc is H3 minus H2, and in the reheater we have heat addition as T5 H5 minus H4. So we have Q in is equal to Cp into T3 minus T2 plus T5 minus T4. Here, since heat addition and net work both get altered due to the reheater, we cannot make a generalized comment at this stage about the increment or decrement in either. But it is sure that W net would increase in the presence of reheater, since the two turbines are added and then they are going to give us more net work. However, since we are having Q in which is also having two components, so a comment about efficiency alone is not feasible at this state, but we can comment about W net, and W net increases with the reheater arrangement, and this is the major reason for which reheater is attached into the Brayton cycle. So let us work out further for optimum reheat pressure. We mean here that we have seen that we do reheating, and the process of reheating starts at the exit of the low high pressure turbine, and then we end the process at point 4. But why this point 4 is here? This point 4 can be here, or this point 4 can be very close to point 3 like this. So there are different ways this location of point 4 is possible. So let us assume at this moment that this is the location of point 4, and we will find out what is the optimum location of point 4. So this is 5 and this is 6. That is what we mean by saying that optimum reheat pressure. And optimum reheat pressure means the pressure at which the W net will be maximum, and then we will find out W net again as WT minus WC, and W net is equal to Cp into T3 minus T4 plus Cp into T5 minus T6 minus Cp into T2 minus T1. So W net is equal to, we will take CpT1 common, and then we will have T3 by T1 minus T4 by T1 plus T5 by T1 minus T6 by T1 minus T2 by T1 plus 1. Now we know that T3 is equal to T5, and we will say that T3 upon T1 is equal to T5 upon T1 is equal to beta. So with this we can write down W net is equal to Cp T1, and this T3 by T1 is beta minus T4 by T1, and then we can write down as expected T4 by T3 into T3 by T1 plus T5 by T1, and T5 by T1 is also beta minus T6 by T1. For that we will write T6 by T5 into T5 by T1 minus T2 by T1 plus 1. So this can be further written as W net is equal to CpT1 as this beta and this beta we can add and say 2 beta, and then this 1 we can bring it here, so 2 beta plus 1 minus, now T3 by T1 is beta and T4 by T3 is separate minus T6 by T5 and T5 by T1 is again beta. So this is what we can write down minus T2 by T1 minus T2 by T1. Now let us see and state that T1 is a temperature ratio which is T3 by T4. We are assigning T1 a new variable as the ratio of T3 by T1, and that practically is P3 by P4 bracket raised to gamma minus 1 upon gamma. We are assigning one more variable T2, which is basically T2 is equal to P5 T5 by T6, and then that is equal to P5 by P6 bracket raised to gamma minus 1 upon gamma. So basically we are saying that this temperature ratio, which is T3 by T4, is T1, this temperature ratio is T2, and we say that now our old RP is T1, which is old RP is T, which is T2 by T1 is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma, and then this is basically the ratio as T. Using this we can do one more calculation. We can say T1 into T2, and then that will be P3 by P4 bracket raised to gamma minus 1 upon gamma into P5 by P6 bracket raised to gamma minus 1 upon gamma. But pressure 4 and pressure 5 are same, so we have P3 by P6 bracket raised to gamma minus 1 upon gamma. But P3 is equal to P2 and P6 is equal to P1. So it is bracket raised to gamma minus 1 upon gamma, but P2 by P1 bracket raised to gamma minus 1 upon gamma is T. So we have T is equal to T1 into T2. So the temperature ratios for high pressure turbine into low pressure turbine is equal to the temperature ratio for compressor. So this we should know, and we should use this for deriving the optimum case. So using this we can further, we should remember this expression, and we will rewrite this expression as W net is equal to CPT1 into twice beta plus 1 minus beta into T4 by T3 minus beta into T6 by T5 minus T2 by T1, and then this for us now CPT1 into twice beta plus 1 minus beta by T1, since T1 is equal to T3 by T4 and T2 is equal to T5 by T6. So we have minus beta into T2 minus T. So here now we have we will say that we are working with same or constant Cp, beta and T. So the variable is only T1 or T2. So we are not altering compressor work, we are not altering the maximum and minimum temperature ratio, we are not altering the working medium. So we are just altering the pressure at which we would be doing the reheat. So here we are just altering the exhaust temperature to the high pressure turbine. So for that all sake we will replace this T2 by T1 and we will say that W net is equal to CPT1, so twice beta plus 1 minus beta by T1 minus beta T1 upon T, since we know that T1 into T2 is equal to T. So T2 is equal to T upon T1. Now let us differentiate this W net with respect to T1 and see what we get and equate it to 0. So the differentiation for this term and also this term will be 0. So we will have differentiation of only this term, which is minus beta upon T1 and minus beta T1 upon T, and then that differentiation is minus beta upon T1 leads to beta upon T1 square and minus beta T1 upon T leads to beta upon T is equal to 0. So this leads to the fact that beta would cancel. So T is equal to T1 square or T1 is equal to square root of T, but we know that T1 into T2 is equal to T. So here T1 is root T, so root T into T, T2 is equal to T. So this leads to the fact that T2 is equal to square root of T1. So it leads to T1 is equal to T2 is equal to square root of T. So what's that practically meaning to us? So this T1, as what we said, is equal to T3 by T4 and that is equal to square root of T. So that is equal to T1 T3 by T1 and also T2 is equal to T5 by T6 and which is again equal to T5 by T1. So this we can solve, and we can feel that T4 is equal to square root of T3 into T1, and here we can get that T6 is equal to square root of T5 into T1. So we ultimately would get T4 is equal to T6 is equal to square root of T3 into T1. So we are having a diagram which is TS diagram, again a special for optimum case, and for the diagram we should have T4 is equal to T6. So these two temperatures should be same. So the exit of turbine, both turbines has to be same, and practically both the turbine pressure ratios are also same, and since both the turbines have same pressure ratio and exit and inlet temperatures are same, so we mean that WLPT is equal to WHPT. Both the turbines are also doing same amount of work in case of optimum Brayton cycle with heat exchange with reheater in optimum case. So now we can find out efficiency. Here we will note down this formula and we can work out with efficiency, and that formula was W net is equal to CPT1 into twice beta plus 1 minus beta upon T1 minus beta upon T2 minus T. So W net in optimum case is CPT1 into twice beta plus 1 minus beta upon square root of T minus beta upon square root of T minus T. So we have CPT1 into twice beta plus 1 minus twice beta upon root T minus T. So this is the efficiency network, and again which is maximum network, we will again write down Q in as what we said. There are two Q ins, and one is in combustion which is H3 minus H2, and one is in heat exchange reheater which is H5 minus H4. So which is Cp into T3 minus T2 plus T5 minus T4. Here again we will purposely take T1 common, so we will have T3 by T1 minus T2 by T1 plus T5 by T1 minus T4 by T1. So Q in is equal to CPT1 into T3 by T1 is beta minus T2 by T1 is T, and T5 by T1 is again beta, and minus T4 by T1 is T4 by T3 into T3 by T1. So we have CPT1 into these two betas would get twice beta minus T minus T4 by T3. So T4 by T3 is 1 upon T1. So we have this as beta upon T1, but we can replace it with optimum case. So for optimum case, Q in is equal to CPT1 twice beta minus T minus beta upon square root of T. So we can write down efficiency as W net upon Q in, where we will write down W net as CPT1 into twice beta plus 1 minus twice beta upon root T minus T divided by CPT1 into twice beta minus T minus beta upon root T. So CPT1 would get cancelled. So we have twice beta plus 1 minus twice beta upon root T minus T divided by twice beta minus T minus beta upon root T. So this is the formula for maximum efficiency in case of Brayton cycle with reheater attachment. So this we can use for two cases. One, we can plot, since the efficiency and network now we have expressed in terms of T, and so we can plot it for different T's, or since we want to express them as pressure ratios, so we can plot them as C, since we have said that T is equal to T2 by T1, which is Rp raised to gamma minus 1 upon gamma, and that is C for us. So practically C is the ratio which we have, a constant which we have represented for pressure ratio. T was the ratio which we have constant we have represented for T2 by T1, but T and C are same. So we get W net if we represent in terms of C for 2 beta plus 1 minus 2 beta upon root T minus T is equal to 2 beta plus 1 minus 2 beta upon root C minus C. Here we can use this to plot W net upon CPT1 and then versus Rp, which is pressure ratio. So we will plot it for different betas. So this is beta 1, so this is beta 2, so this is for beta 3, and this is for beta 4. So here as well, at higher pressure ratios we can see that the network decreases. This is CW net upon CPT1. Now we can go back and write down the formula for efficiency in terms of C, since we have represented earlier that formula in terms of T. So Q, so efficiency for us, if we read down in terms of C, then efficiency T will be replaced by C. So efficiency corresponding to maximum work will be twice beta plus 1 minus twice beta divided by root C. Since we have said it as root T, so it will be root C minus T. We'll just go back, and here this T will be replaced by C, and this T will be replaced by C, this T will be replaced by C. So in that way we have here C divided by twice beta minus C minus beta divided by root C. So here as well we can see twice beta minus C minus beta upon root C. So these things would make the new formula for efficiency, which corresponds to maximum work, and we can plot the efficiency versus Rp for Brayton cycle with reheater. So efficiency versus Rp, and here first again we will plot efficiency for the Brayton cycle without reheater, and as what we said, with reheater, since we are adding A reheater, we are adding more heat. So this is the efficiency for beta 1, this is the efficiency for beta 2, and this is how efficiency increases with increase in beta, but at lower betas efficiency is lower than the without reheat cycle. So this is the understanding for Brayton cycle with reheater and Brayton cycle with heat exchanger. Rest of the attachment and associated performance alteration we will see in the next class. Thank you.